In this video, we're just going to compute the Laplace transform of 2t minus 1 times the Heaviside function at t minus 2. Now notice we've got a function of t times the Heaviside function at t minus 2. That means I am going to use this entry in the table. We've got the Laplace transform of g of t times h of t minus, or a, excuse me, is equal to e to the negative as times the Laplace transform of g of t plus a. So typically I would go to the table and I would try to find an entry that matches this. So here's my table, and if I keep scrolling down a little bit, and I want to zoom in as well, if I look for the Heaviside function, which is denoted by a u on the table rather than an h, entry number 53 is relevant. So it says g of t times u of t minus a is e to the negative as times the Laplace transform of g of t plus a. So that's number 53, and that's what I've written down here on my paper. So we're just going to do some pattern matching in order to apply this. This is g of t, and this is h of t minus a. So the first thing that we want to do is identify g and identify a. So we know that g of t is 2t minus 1, and if h of t minus a is equal to h of t minus 2, then a must be 2. After we've identified a, I like to substitute a into the right-hand side of the equation. So we're substituting into the right-hand side of that identity. So, excuse me, this identity says that under certain conditions, this expression is equal to e to the negative as, where a is 2, so we'll substitute in 2 there, times the Laplace transform of g of t plus a. If a is 2, that's going to be g of t plus 2. So I've got a g of t here. I need to find g of t plus 2 next. Just by substitution, we've got 2 times the quantity t plus 2 minus 1. So I'm just using placeholder notation. This takes something, it doubles it, and then it subtracts 1. So instead of a t, we're going to input a t plus 2. We're going to double that, and we'll subtract 1. We'll distribute the 2, and then collect like terms. And then we'll substitute that into the right-hand side of the equation as well. Okay. And then the last thing we need to do is just compute the Laplace transform of this and make sure you keep that e to the negative 2s right there. So we'll have e to the negative 2s times the Laplace transform of 2t plus the Laplace transform of 3, because the Laplace transform is a linear operator. Now, we have some entries in our table that say that the Laplace transform of 1 is 1 over s, and the Laplace transform of t to the n is n factorial over s to the n plus 1. So in this case, this is just going to be 3, which is a constant, times 1 over s. So that'll be 3 over s. And then here we'll have 2 times the Laplace transform of t to the first. Well, that means that n equals 1 when I'm matching this pattern. So I'll have 1 factorial over s to the 1 plus 1, or s squared. And that's sorry, my Zoom window closed for a second for some reason, which was odd. Okay, e to the negative 2s times this plus this. And that's it. So we just identify G and identify A. Substitute into the right-hand side of the equation. And then the right-hand side really tells us what to do. It says, find G of t plus 2, then take its Laplace transform and multiply it by that. So we evaluate G of t plus 2. We compute its Laplace transform, and then we multiply by that. Easy breezy. But the entries that we need in our table are entry number 53, and these two, which are pretty basic, and I don't remember which entries those are in the table, but they come up so often that I have them memorized. You don't have to memorize them, though. They are at the beginning of the table, probably in entries like 1 through 7.